This question is asking second order PLL is implemented with a non-ideal loop filter. H of s is equal to s plus a over s plus b, in which b is greater than 0 and it's very small. A part is asking apply small signal analysis, determine the transfer function between theta e of s and theta I of s. Okay. Now let's look at the equation that is given for the transfer function. PLL, I'm doing the A part of this. PLL transfer function is given by theta E over theta I, and theta E is calculated using Kp Kv times h of s, and theta I is s plus Kp Kv h of s. Okay, and here Kp represents the phase detector gain, and Kv represents the PCO gain, and h of s represents the loop filter transfer function. And h of s is also given that's equal to s plus a over s plus b. So now we have the h of s value. We have the equation for the transfer function, that's theta e over theta I. Here instead of this h of s we can substitute this one, and let's see what happens. Okay, I'm gonna go ahead and continue this on my next page. So let's copy the equation. We have theta e over theta I, theta e over theta I, that is equal to kp kv, and instead of h of s I can plug this one right here, that is s plus a over s plus b. And in the denominator we have s plus kp kv, s plus kp kv, and then instead of this h of s we plug this one right here, that is s plus a over s plus b. Now let's try to simplify some terms. So here in the numerator we have kp kv, and I keep the s plus a in the numerator, and if I bring the s plus b, this is like if you have 1 over a, you can bring the a to the denominator and multiply everything. Same thing goes to this. If I bring the s plus b and multiply the denominator with that, then that will help us to cancel this s plus b. So that's going to be s times s plus b, and then this one times kp kv, and this s plus b will cancel because we are multiplying both of them by s plus b. So this is going to be kp kv, and then that's going to multiply by s plus a. Okay, so this is what we have right now, and here we can do another thing to simplify this one furthermore. Like we can take the kp kv command. If we do that, we keep the top one as it is, that is kp kv times s plus a, and here in the denominator we can expand this one, that's s square plus b, and then I take the kp kv command, but if I do that, then if I take the kp kv command, then s plus a is gonna remain the same, Okay, and then for this one we are going to have a square plus b sb. If we expand this bracket right here, and that one should be divided by kpkv, because that doesn't have a multiplication of kpkv. So to get this one when we multiply back, to get this one back when we multiply, we have to put a kpkv in the denominator, and now it's good. Okay, the next thing is we can cancel this kpkv. That's the reason we take it outside. So let's go ahead and continue here. So if we simplify this one furthermore, now we have s plus a, and then s plus a plus s square plus sb over kpkv. This is what we have right now. But here, simplifying this one furthermore helps us to eliminate something like there's an information provided in the question, that is in which b is greater than 0 is very small. It means b is like almost close to 0. So we can use that information to get rid of something from this one. Let's see how we can get that. So I keep the top as it is, s plus a, and the first term has s plus a. Okay, in the denominator we have s plus a, and okay, let's keep the a outside, and we have we can separate this s square over kpkv. Then we will end up with sb over kpkv left, and also we have an s. So what we can do is we can take the s common for both of them, so that's going to be 1 plus, and then if we take s common for this one as well, this is going to be b over kpkv. Okay, I think it's better to write right here. I'm going to erase this because it's not very visible. S plus a over a plus s square over kpkv. This one is v, and then plus s. I'm just copying this. S1 plus v over kpkv. Okay, this one is derived by simplifying this. I want to get rid of this to avoid confusion. Just copy this one and put it here. Now from this one you can see this part here, 1 plus kpkv, 1 plus b over kpkv. We know that b is a very small number, right? Let's mention it again. B very small. Hence this part 1 plus b over kpkv, that one should be approximately 1, because we are dividing a very small number by a constant value. It can be bigger or whatever, but it's reaching 0. It's almost 0. So we can say approximately this term is 0. So when we add that one with 1, that should be giving almost 1, because if you add 0 with 1, that's going to be almost 1. That's going to be 1, but it's close to 0. You cannot say just 0. Close to 0, so that's approximately 1. So by doing that, we can just get rid of this, because this is going to be just 1, and then the s is going to be left, because if you multiply s by 1, that's going to be s itself. So s is going to remain the same. Then we are going to have s plus a divided by a plus s square over kb kv, and then plus s. Okay, Now that's what we have. Okay, and we can do another thing. If you want to bring this kpkv to the numerator, you have to just multiply top and bottom by kpkv. So you will end up having this. I go to next page and write that one. So the transfer function is, if I multiply the top and bottom by kpkv, then this is going to be kpkv times s plus a. And in the denominator, we are going to have kpkv times a and plus this kpkv is going to be cancelled. So this is going to be just s square right here. And then this one kpkv times s. Okay, that is the final transfer function expression. Okay, that is for the a part. Now let's look at the b part of this question. The b part of the question is asking, find the steady state PLL phase error for an incoming phase. Theta I of t is equal to omega naught minus omega c times t plus phi naught. Let's rewrite that equation. I'm doing the b part, and here the given one is theta I of t, that is equal to omega naught minus omega c t plus phi naught. Now in order to solve this kind of problem, to find out the steady state PLL phase error, it's good to convert this one into Laplace domain, and then we can solve it. So we have to find out the Laplace transform of this one. If you do the Laplace transform of this theta I of t, that's going to become S domain. So this is going to be theta I of s right now, and then if we have a t, that's going to divide by s square. So omega naught minus omega c divided by s square, and if you have a constant, that's going to be divided by s. So this is going to be phi naught divided by s. And finally we derive this one, like you can take s square common for both of them, but if you do that, since this one has s only, you have to multiply the numerator by s. So this is going to be omega naught minus omega c plus phi naught times s divided by s square. Okay, this is theta I of s. Now there's an equation that theta E of s, that is transfer function multiplied by theta I of s, and the transfer function we already derived right here. So instead of this transfer function, we can just replace this one with this. So that is kpkv times s plus a divided by kpkv times a plus s square plus kpkv times s, and instead of theta I of s, we can plug this value, that is omega naught minus omega c plus phi naught times s divided by s square. Okay, now for the steady state, we have to use the final value theorem. For steady state, and final value theorem is analyzed in when t approaches infinity in time domain, but in Laplace domain, that is when s approaches 0. So this is the one helpful for us, because now we are having everything in Laplace domain. So we have to apply the limit s approaches 0 and substitute the values and see if we can get directly. So let's go and do it in the next page. So theta E steady state limit s approaches 0 And if the limit s approaches 0, let's see what happens here. So for the first one here, if I substitute 0 for the s values, this is going to be 0, so we are going to have a kp kva on the top. Okay, if I substitute, I had to get it, I shouldn't put the limit anymore. Let's remove this. But first I have to express before I apply the limit. I didn't express it yet, so I had to write a whole thing first. Limit s approaches 0, and then this whole thing, kp kv plus a divided by kp kv times a plus s square plus kp kv times s, kp kv times s. Okay, that is for the transfer function, and then we have this one as well. That is omega naught minus omega c plus phi naught s divided by s square. Okay, that is what we have. Now if we substitute 0, then this is going to be 0 right here, and then this term is going to be 0, this whole thing is going to be 0, so we are left with this two term. And then for this one, this is going to be 0 and this is going to be 0, so we are going to end up with okay, let's write it here. So this is after applying the limit. Okay, so I can really cancel right away like this because I'm not applying the limit yet. So I'm just showing this, these are the things going to be 0. So after it all becomes 0, then this is going to be kp kv times a part left, and in the denominator also kp kv a part left, and in the other side we have omega naught minus omega c left, and the denominator is going to be 0. So this one is same value, so these two are going to cancel, so this is going to be 1 times, if you divide any value by 0, that's going to be infinity, so we are going to get an infinity value. Okay, so that's our answer for the B part. Okay, and let's double check the question. This is that, and PLL error. Yeah, we found both of them, and that's it. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.